Welcome to SanfordFlipMath. This is AP Calculus. We are working from the Finney, Demana, Kennedy book for Calculus, AP, third edition. And we are working our way towards something called the fundamental theorem of calculus. We have already done some dabbling with this. In fact, I'm about to recap the exploration that we did as an activity in class because I think the point that comes from this is so huge, and since I don't do an actual proof for the fundamental theorem of calculus, this is as good as it's going to get for us. So this is kind of a recap of exploration 2 from page 289, which kind of illustrates what's going on. And so what we've done is copied the graph, a rough shape of the graph from the book, and we're going to do a little shading. And I'm just going to pick an x value right here, and we're kind of doing some shading that kind of fills in this curve. And what's shaded here, I'm going to call this point x. And what we've just shaded in is the area from a to x, the integral from a to x of f of something d something. Now, the catch here is that I can't call this f of x because I'm using this as x. And what I'm doing is giving another function that is called capital F, and it is capital F of x. And what I'm saying is that this is kind of like the area. Now, I'm using this term area kind of loosely because integral doesn't have to mean exactly area, because it could mean a positive area and a negative area that kind of combine and things end up canceling out. We've talked about that before. Okay, but the idea here is, so I have to call this something else. I'm going to call it t. That's kind of the common thing to call it. It doesn't have to be t. It could be q. It could be u. It could be anything other than x. Okay, so what this represents is that area that we've added up, and picture it by adding up a bunch of rectangles or something like that. And now what we're going to actually do is focus in on kind of like one specific rectangle right toward the end of where this shading happens. So I'm going to look at one little bitty rectangle here, okay? And this one little bitty rectangle, okay, is like the last little rectangle, okay? And its width is going to be dx, okay? So it's kind of like if I did just a little bit more shading, I would go a little bit more to dx, okay? And the area that we've just done then is this last little bit that we're adding on would have to be df. And the area, that area, would be length times width, or base times height, delta x, times whatever this height is. Well, this height is given by the y value. Well, the y value is given by f of x. Okay, f of whatever that x value is. Okay, so what we're going to do then is just say that that was the height, so times f of x. Okay, and then we're going to take that last little bit that we just wrote down, and we're going to solve this so that we can figure out, I want to solve it for f of x. So f of x equals, I'm dividing by delta x, delta f over delta x. Now, as we've done some calculus, and we know some calculus notation, if this was an infinitely narrow delta x, then we would make that dx. And this would be df. So in effect, f of x equals f prime of x. Okay, so this has huge implications, and this illustrates the idea of, well, first of all, that the derivative, I'm letting the cat out of the bag out there, the derivative of the integral is f of x, in other words, y. It also means that if I were to undo the integral, or I'm sorry, if I were to undo the derivative, f of x would be equal to the integral of this little guy. Okay, so the derivative of the area is back to the original function, and the integral of the function is the area. Okay, so here it is. Now again, we've talked a bit in class about how Newton was working on integral calculus, and Leibniz was working on derivative calculus, not even knowing they were working on two ends of the same thing. And this is the theorem then that connects it all together. And to me, it's just pretty darn exciting that they were working on stuff that they didn't realize they had anything to do with each other, and there it was. Pretty cool. Okay. All right, so this is the fundamental theorem of calculus as is stated. Okay, this is a big deal. Part one. So capital F of x, this is that area, the idea of area. Okay, that concept is the antiderivative of f of t, whatever the y value curve is. Okay. So similarly then, if I do the derivative of that, okay, the derivative of the integral. Okay, so here's the derivative of the integral. I'm back to the original. Now, check this out. See that how that's a limit of integration, and basically it pops in there to replace the t. Okay, so just be aware of that. When we're doing the derivative with respect to x, it pops in there. And there are going to be some chain rule issues that can come up with that. Okay, so be watching for that. Okay, so that's part one of the fundamental theorem of calculus. The other part is the part that we've kind of already been doing, you know, so this is kind of like old hat. Basically, do the antiderivative and then substitute this guy in and substitute that guy in and subtract. Now, technically, when you do an antiderivative, there's a plus c that happens on both of these. And when you subtract, the plus c's end up canceling out. So we almost never do the plus c when we're doing what's called a definite integral. Definite integral. A definite integral just means an integral with endpoints. Endpoints. In other words, the a and the b. Okay, I don't need parentheses, but I did anyway, sorry. An indefinite integral is basically just antiderivative, and that requires the plus c. Okay, okay, so no c required for a definite integral because it subtracts away anyway. All right, let's look at some specific examples that deal with the first part of this rule with the derivative. So this is going to be it's kind of cool, but it's kind of funky. Okay. Okay, so here are a couple of problems freshly borrowed from page 302 from your calc book, and please note the directions say find dy dx. Okay, so I don't want you to freak out because these problems are actually pretty darn easy. But along the way, I want to point out a couple of things. Okay, so really, if we go back to this rule up here at the top, okay, and so the rule says if I do the derivative of the integral, basically the derivative and integral just kind of cancel each other out since the integral is an antiderivative. And notice that here's this a here, and a doesn't appear in here anywhere. Think about why. It's kind of bizarre. I mean, to me, it's not expected. Okay? So in other words, this 2 has nothing to do with the answer. And basically, again, we're going to do derivative, so dy dx. Okay, notice this is x, cool. Okay, so we're doing derivative with respect to x. This is just going to equal 3 times x plus cosine of x squared. Now, when we've done antiderivative, we had to plug in the x, we'd plug in whatever b is, right? Minus plug in whatever the a is, right? Now, keep in mind that what we're doing is the derivative. So if this is a constant, and we were subtracting this with the constant in it, and then we did the derivative of that answer, that would be the derivative of a constant, that derivative would be 0, which is why it doesn't matter. Okay, so rewind it, listen again. That was probably about 15 seconds worth of gibberish, and that's it. Okay, so quick note here, derivative of the integral, yeah, we're done. That's it. Okay, number 8, this constant does not matter. Derivative, once I substitute it, the derivative of that answer would have been 0 anyway, okay? So again, I'm doing derivative of this with respect to x. This is x, cool. Okay, really just rewrite it with x substituted in. I mean, I wish there was something more exciting to do with this, but honestly, that's it. The concept here is the half of the fundamental theorem of calculus that we're working on is this idea that the derivative with respect to x of the integral going up to x is back to whatever the inside was, whatever the integrand is, whatever that argument for the integral is, okay? All right, well, let's do some more of that. There are some issues that can come up, okay? Okay, so let's deal with what comes up. Okay, so again, we're still doing dy, or d of d dx of this, dy dx. Okay, so now here we're doing derivative with respect to x. This is a little more interesting than x. Okay, so let's go ahead and do the first part of this. We are just going to substitute this in. Here's the catch. We're doing the derivative with respect to this whole thing, but now this is on the inside. So technically, what's happening is when I'm doing the derivative, I still have to multiply by the derivative of the inside. Now, this is the inside that I just put in there. So I have to multiply by the derivative of the inside. There is a chain rule part that comes up with this, okay? So if there's something here that's not just x, you have to multiply by its derivative. And that is something that, okay, you'll remember it this time, but will you remember it on the test, and will you remember it more importantly on the AP exam down the road? That's tricky, okay? So be careful, okay? One more thing that's kind of similar. Now notice that every one of these had the constant on the bottom. Oh, that's not the constant. That's the variable. So what do we know that is the constant though? When I switch these, what's that do to the integral? So supposedly this whole thing should just look like 2x squared plus x plus 1 in parentheses, or in a square root. But when I switch the limits of integration, that's negative. That's it, no big deal. Okay. Okay, so this is going actually backwards. Okay, so just a minute ago, you had something that looked like this. Maybe more so like this. Okay. So, and what we did was we did the derivative of it, and we got something that looked like that. Okay. Well, we want to go backwards. Okay, so what we're going to do is write y equals, and then there are a couple things. Well, first of all, we're going to go from something to x. We just don't know what something yet. And as far as the function itself goes, it's going to look exactly the same, only it's not going to be x's. Okay, so now the only question is, what do we do with this stuff? Well, this x value is actually just that x value. And this y value is just a constant that could have happened. And honestly, that's it. Yep, that's it. Okay, let's do another one exactly like it, only completely different. Okay. Ta-da! Yep, there it is. All right, so follow the same pattern. We're going to say y equals, now this time it's going to be the integral from something to x of e to the square root of not x, d not x. Then the only other stuff is, here's x equals 0 and plus 1. And the idea is this is like an initial condition that establishes that value. And really, that's it. Okay, so going backwards is just as easy as going forwards. Actually, it's even easier because you don't really have to worry about the chain rule part so much, because you can account for it with just the t. Okay, and just putting x. So that's pretty straightforward stuff. Okay. Okay, I want to do one more thing, and I probably said that last time. And the main reason is that I want to deal with this part, because we've just did a bunch of that stuff. But the beauty of it is we've already done this before. So what we're about to do should not feel that new. Okay, so we're going to work with part 2 of the fundamental theorem of calculus. And the only thing that's going to really make this feel new is the equations are going to get more complicated. Okay, so 2 to negative 1 and 3 to the x dx. Okay, so the process here, we're going to do antiderivative, and then we're going to start plugging stuff in. Okay, now this is where things are going to get a little more interesting. I'm going to have to use the T word, and I know you hate that, and I'm sorry, but you're going to actually have to think. And part of the issue is, the question is, if y was 3 to the x, what's dy dx? We're going to have to remember some derivative rules and then think about how to do them backwards. Like, if y was 3 to the x, dy dx would be 3 to the x, but times the ln of 3, the natural log of 3. And I don't see a natural log of 3 floating around here. So how can I make it so I'm doing the antiderivative and I get, you know, when I do the derivative, I need to get this. Remember, I'm trying to undo derivative. Undo derivative. What did I take the derivative of? Well, if it was just 3 to the x, I'd have this. I don't have that. So I really need that to cancel out somehow. So what if I originally started with that? Okay, recap. If I have y equals 3 to the x over the natural log of 3, this is just a little constant. This 1 over natural log of 3 is a little constant that comes along. So y prime would be 1 over the natural log of 3 times, that's just a constant that's coming along. Derivative of 3 to the x would be 3 to the x times the natural log of 3. Those divide out. That's cool. All right, so here it is. 3 to the x over natural log of 3. I need to evaluate this from 2 to negative 1. I need you to start using proper notation. This is proper notation. So I haven't evaluated this yet, so I need to represent that I need to evaluate this. And you know, I'm seeing on, you know, so far on tests and stuff, I have not seen proper notation. Now, if you're looking at this in 2014, 2015, then maybe I just, you know, I'm getting on your case and it was really for 2013. Yep, you can point fingers at them all day. Sorry, it's their fault. Okay, so now I'm going to substitute values, and remember, it's always the top number first and then the bottom number. So 3 to the negative 1 over the natural log of 3 minus 3 to the second over the natural log of 3. And then it's just a matter of simplifying this. Okay, so this is a lot of fun, right? Since I have the same denominator here, I'm just going to kind of put this together if that's all right with you. 3 to the negative 1 minus 9. I don't know, this is just an ugly mess. Maybe I didn't want to do that. I don't like it. And I can't rewind with the recording software I'm doing, sorry. How about this? All right, so 3 to the negative 1 is 1/3. So in effect, I just kind of flip that to the bottom. I'm going to multiply the top and bottom of this by 3. Okay, almost done with this problem. Okay, so this is going to be 1 minus 27 over 3 natural log of 3, negative 26 over 3 natural log of 3. I'm actually kind of okay back here, but as you know, if we have a multiple choice question like this, the answer is never going to look like that. Checking answers in the back of the book, it's never going to look like that. So if it's a calculator problem, then you could just type that sucker in way back when, so that's fine too. Okay, I just want to do one more problem like that, same idea, just one more problem. Okay, wouldn't be Mr. Sanford if I didn't go at least 20 minutes. So, and here comes 20 minutes. Okay. Okay, this problem is actually significantly easier. It doesn't look like it right now, but it is, trust me. Okay, so in fact, I'm going to make it easier by rewriting this as 2x to the negative 2. Now, I know some of you right now are probably thinking, I would have never thought to do that. Well, you will, because we just did an example to show you that that's a way to do it. Okay. So here we go, -2, oh, I don't want to do that. Okay, I want to do antiderivative now. Okay, so I'm going to do, I need to add 1 to the exponent, and I need to divide by the new exponent. So -2 plus 1 is -1, and then I'm dividing by the new exponent. Okay, so remember that rule that we just did is basically x to the n plus 1 over the new exponent. Okay, and there's a constant, that 2 is just coming along for the ride. Okay, proper notation from -2 to -1. Okay, can I get just, no, of course not. I just wanted to get rid of that little underlining thing, but whatever. Okay, I'm going to rewrite this as -2 over x because it just looks better to me. I haven't done this yet, so I still need to represent it. Okay, so again, top one goes in first. -2 over -1 minus -2 over -2. Okay, so this is just 2. Now, be careful. -1 is 1. Huh. I've never seen a calculus answer just come out to be just 1. I mean, how cool is that? All right, so we did a lot of math here. First of all, derivative of an integral, back to the original function. If what you're substituting in, if that instead of just x at the top, it's something more complicated, you have a little chain rule. Okay. If you're going the other way, just rewrite it, and just keep in mind if it's saying, okay, so I'm talking about this kind of stuff. If you're going backwards, then the y value is that constant, the x value is where the integral started. Okay, and then we've been doing this for a while, the antiderivative thing to find integrals. It's just now we have a reason that says we can. Okay, well, thanks for watching. Thanks for hanging with SanfordFlipMath, and we'll see you in class. SanfordFlipMath out.